Okay, so I'm going to at least try to explain kind of how to solve some physics problems. Basically, because right now I'm learning physics too, so I figured as may as well, if I try to explain it, I'll learn it too. Well, so everything will basically be based off, where is it? This book. So I think it's a pretty common one this is for AP Physics 1, by the way, right here. So everything will be based off this book. So I'm basically going to go over for chapter kind of 4, 5, 6, because that's the test for me that's coming up. And that's basically, like all the like all the forces and shit. So to do that, let's look over some kind of typical questions that are obviously going to be on the test, which would be, let's see, that one, this tab right here. All right, so essentially the main thing about to do with like forces is you just have to remember F equals ma. Now, I know that sounds pretty basic, because it is. But the thing is, like, F equals ma, or to be more exact, F net, because net force equals ma. Essentially, that's saying that that's already adding up every single force. So the reason is why that's so like it encompasses everything is because you're never gonna leave it like this. You're gonna say F net equals ma, which sometimes is gonna be equal to the tension force minus the friction force, or it could be equal to just the tension force. You don't know. Essentially, that's the F equals ma is extremely, extremely broad. So in order to do anything, you need to look at the problem and decide what is my free body diagram going to look like. Free body diagram basically just shows all the forces. So let's look at this one. Child is playing with 3 blocks connected by massless strings as shown at the right. Applies a force of 12 newtons to the 2.5 kilogram block and makes all 3 blocks slide to the right on the frictionless surface. So first thing to notice, there is no friction. That already takes out one force. So you look at what are the forces in this case. So first things first, because in the end, like strings are these are massless strings, we can assume that basically the whole thing, basically this whole thing, is one big system. So let's assume the whole thing is one system. So what does that mean? So we know that you applied 12 newtons tension force. So this is one of the forces. And notice that there's no friction force, which means the net force is going to be 12 because there's no friction to hold it back. So the only force really that is not like balanced out is 12. Because yes, you also have gravity, mass times gravity, so you have your weight, but which goes downward, but that's going to get balanced out by the normal force, which is perpendicular to the surface. So let's basically start. You have 1, 1.5, and 2.5. Okay, so drawing our feet. So essentially we've got, F net equals ma, which in our case is equal to, m is 1 plus 1.5 plus 2.5. Right? So you have that times a, because we don't know what acceleration is. And we know that that's equal to 12, because there's no force going backwards, so the net force is 12. So you do that. So now let's find what acceleration is. So 12 divided by 1 plus 1.5 plus 2.5, which is equal to 2.4. Giving us an acceleration of 2.4 newtons. Or not newtons, 2.4 units. So like, I know like teachers are going to say, oh, units really matter, but honestly, you don't really need to know them until the end, because you're going to it's going to be pretty obvious, because they're asking about acceleration, you know the units. You don't really have to worry about them through the middle and shit, because then it's just, since force is the question for 13, our answer is going to be newtons. Yeah. So, what do we do now? Well, we found the acceleration, and one thing you have to realize is that the acceleration will be the same for every single one of these blocks, which now lets us basically split this one big system into multiple systems, because we know that the acceleration will be the same. So the question is, what force is exerted on the 1.5 block by the string connected, oh, this typo, to the 1.0 block. So we're essentially trying to find, if you look at my cursors, we're trying to find this force right here. This force, basically going from the 1.0 to the 1.5, which is basically the tension force of the string right here. So notice again that there's no friction, which means that the tension force, again, is our net force. So let's define a new system. New system being the 1.0 block. The 1.0 block has f net, which is ft in our case. So we have that, and we know acceleration is 2.4, which means, and sorry, we'll call this f net 2, because this is the first one was different. First one is for all three blocks. So we know f net 2 is f tension, so we say f net 2 is equal to, of course, m times a, as always. In our case, though, our n this time is just 1 times the acceleration, as we said before already, was 2.4, giving us an f net 2 of 2.4. And we said f net 2 equals ft, which right here, and that is the force that we're looking for, because that's the force that is exerted on the 1.5 kilogram block by the string, because that's the only force that's coming from the 1.0 block that isn't balanced out. Because, as I said before, there's mg, but that's balanced out by normal force. Because the way you know that is the block isn't sinking, which means that the force that's going downward must be matched by an equal and opposite force going upward, which is Newton's third law. So, by the way, this isn't like, you should actually have studied this stuff before you look at this. This is just to show like how to do the problems that are going to be on the test, at least for my teacher, and this will probably be it's pretty common since AP Physics, so the curriculum is pretty similar. So you'll probably have stuff like this on your test too. So we have that. That's pretty simple. Our answer would be 2.4 be units, so 2.4 newtons to the right. Great, we found the answer to the first one. Erase the whole thing. Try that. Clear current page. Oh, nice. Okay, let's do another problem. Okay, let's do one item number 4. Alrighty, we're going to try, this looks boring. This is like apparatus and stuff. Let's just do, this is gonna be a fun one, isn't it? Oh, this is so easy, just draw a free body diagram. Alright, well, we can do it. So, draw a free body diagram of the box, which is pretty important, because essentially everything is based off a free body diagram and F equals ma. You need to know those two things. So, a 20 kilogram block is placed on an incline that makes 35 angles to with horizontal. Let's draw it out first. Horizontal, 35 degrees. We've got our 20 kilogram box. 20. And the coefficient of kinetic friction between the box and the incline is 0.25. Okay. And the box slides when it's released from rest. So the bright side here is it says that it slides when it is released from rest, which means we don't have to check whether the box slides or not. Because normally you need to check whether it'll move, and then you decide whether you're going to use static friction or kinetic friction. So let's draw a free body diagram of the box. You're going to have your normal force, which we're going to have our mg this way, and I want us to label each word as algebraic symbol and numerical value. What? All right, so you have to find. Okay, you actually do have to find the numerical value. Cool. We have that, and then we've got. So remember, which way is the box going to slide? This is not a trick. Obviously, it's going to slide downward because there's no force pushing it upward. So if it's going to slide downward, then which way is friction going to act? In the opposite direction. So the box slides that way. That's sliding that way. Then we know this way is going to be our force of friction. And in our case, because we know it slides, force of kinetic friction. So we've got kinetic friction and we've got a force that way, which is the way it's moving down. Now the first thing we need to do is find kinetic friction. So if you guys remember, the equation for kinetic friction is the basically mu. How do you write the symbol? It's like a weird U kind of. It's like that times the normal force, which is not how do you draw that one. Times Fn. Cool. But now this is another problem. We know what U is 0.25, or is it? Yeah. But what is the force in newtons? Or not newtons, what is the normal force? So if you guys remember, another equation we know is normal force is going to, and here's the tricky part, it's not mg. People always think, oh yeah, normal force is always going to be mg. That's only if your surface is straight. If it's, and on a ramp like this, then it's actually, and here's the interesting part, we're going to do that. So you're going to think, okay, so what you have to remember is this right here, that's 35 degrees. Because we're basically taking our coordinate and shifting it so it's going to look, so it's looking like that and that. Almost like x-axis, y-axis. Erase that, erase that. So we know that part's 35. What the heck? Okay, yeah, so here's the thing. We know what the angle is. You have to remember that there are two sides in this part. Let me erase this so you can still have clear. Yeah, so as I said here, it's mg downward. So we have this, and we have that, and we've got that being 35. So what is this? So this is just a regular trig problem. You have a triangle here. You've got, this is our little 90-degree angle. If that's 35, what is this part? What is this part going to be? Because you have to remember that this part, that's the part that's opposing the normal force. So that's what normal force is going to be equal to, which is actually, interestingly, is your mg times, or it's the mg times the cosine of 35. The reason being that our triangle basically looks like this. Basically looks like mg and 35 degrees. So this part right here is mg cos 35. This is mg sine 35, which is really weird because, normally you always think, oh, wait, sine is the one that's usually on the top part, and cosine is the other way around. But like when you're looking at it here, but it's like this in this case, because you have to remember, as my teacher always says, math is a tool, physics is what uses it. So let's find the normal force. Mass is 20, so 20 times 9.8 times cosine 35. Let me just do my calculator. We get 20 times 9.8 times cosine 35. Okay. So Fn is 160.55. That's cool. Sorry, hang on. Alright, so now that we know our normal force, we can find our kinetic friction, if you guys remember. So so we need to do that part first. So our kinetic friction is, now we know it's going to be kinetic friction equals mu, which is 0.25, times the normal force, 160.55. So 160.55 times 0.25 is going to be equal to 40.13. So friction kinetic equals 40.13 newtons that away. So now we have one thing, but now we need to find what this is. And here's the thing, we know that it's going to slide down, so we know that this wins. So if you remember what I said at the beginning, everything in the end is all based off F net equals mass times acceleration, and F net is just the sum of all the forces. So in our case, F net, since it's moving, it's going to move that way, that way. So from here to here, there to there, we know that wins. So we know, let's call that force. What should we call that force? Let's call it force. Like F moving, whatever, FM, who cares? That minus Fk. Because we know that that wins, so that we know this is greater than Fk. So if you take that and you subtract Fk away, that's how much it's actually moving this way. And that's our F net. So we know if you remember, so we think, okay, well, we have we only have Fk, but we don't have F net or Fm. But remember, F net is m times a, and we do have that. The reason being, I just screw up. Hang on. Give me a second. What was it doing? 20 program box. I'm trying to find that. F of k. F net is the mass box. Well, that's not the best thing. Oh wait, no, actually no, it shouldn't be too hard. It's just oh yeah, sorry, what am I saying? We actually do have Fn or FFM, Because if you remember how I was showing the diagram here, right? How this line here gets opposed by this. But you have to remember, mg has another vector, which is right here, that part. Best way to see it right here, so that part right there. And that's the part that basically moves it, that's parallel to the surface. So the way you want to remember it is, if it's perpendicular to the surface, that's going to be the normal force, and if it's parallel, that's the one that's actually moving it. So in a way, this is just, so we can really write this as Fmg parallel force. So let's find out what that is. This is equal to, what is that force of mg parallel? We wrote it right up here. mg sine 35 minus the friction of kinetic is 160.55. So what's that? Let's see, 20 times 9.8 times the sine of 35 minus, wait, Fn isn't, no, Fk is, whoops, not, minus Fk, 40.13, sorry. So you take that, basically mg sine 35 is 112.42, because 20 times 9.8 times 35. Subtract 40.13 from that, and we have a wondrous beauty of 72.29. So we have 72.29 is basically our F net. And if you remember, now you may think, okay, well, what is the point? Because like, look at the question. The question was asking, what is, like, draw a free body diagram of the blocks, label each force with its algebraic symbol and numerical value. So really, I guess you don't need to do that, because you can basically just draw this. We've found Fn, we've found mg, we found Fk, and we know this F as well. This last one, which is Fmg parallel. So we basically found the entire thing. So again, pretty basic problem. And if you remember, everything's based off F net equals ma. Let's see, what's an interesting one? Oh, let's just do this. Let's do a little, should we do a circle one? Circle one could be pretty cool. Okay. If a child is playing with a toy comprised of a massless 85 thing, and he's going to a vertical circle at a constant speed, important to know, tension of string is 2 when the ball is at the bottom of the circle and moving sideways. Right? Our age-old free body diagram. We've got a little ball. First we draw the thing. We have a little ball with a string like this, and that's not our free body diagram, that's the actual diagram. So let's draw a free body. We have a ball, we have two forces. We've got our mg, because remember there's no angle, and we have an upward force of ft. So now you're thinking, okay, why is tension upward? The tension force is always along the string, and if you look at our picture here, this is where the string is, because that's where my hand is. Oh, my hand. So the tension force is always going to be up at the string. But let's say the ball was up there instead, for example, then tension is going downward, because it's always going to go, in this case, towards my hand. It's always going down or up the string. So we have force tension, we have mg, and that's what we have currently. So now the question was, what is the speed of the ball? So speed of the ball. So let's look at, okay, what are the equations? Usually they'll probably have in this. So the speed of a ball is basically asking for the final, I guess, acceleration, or final velocity. Or I guess, or no, really the best thing to do is, you look at this. So you notice how it says spinning in a vertical circle? So if you see a circle like this, you're going to know one thing. It's going to do with centripetal acceleration and centripetal force, because that's basically what all the circle problems are. So, because I'm basically just going to show like how to solve these problems on tests, and you're going to know if it says circle, it's going to be either centripetal acceleration or centripetal force. So we look at these equations. Centripetal acceleration is v squared over r, and centripetal force is m times ac, because remember F net equals ma. So let's do our beautiful little equations. We have F centripetal force equals m times ac equals mv squared over r, because ac equals v squared over r. So now we say, oh look, wow, there's a little v there, because that's what we want. So in order to do that, we need to find everything. So the question is, what is centripetal force? In our case, centripetal force is essentially the tension. So like you look at, okay, centripetal force, is always going towards the center of the circle. So which way is center of circle? And since the ball is down here, center circle is upward, which means the tension force basically is greater. So it's going to be equal to the tension force minus mass gravity. And what's that? Well, look at the question. Tension force is 2 minus mass gravity. The mass gravity is, let's see, what's mass gravity in our case? The mass of the ball is 0.08, 0.08 times 9.8, 0.784. To 2 minus 0.784, that's going to be equal to 1.216. Yay, 1.216 is our centripetal force. But that's not what we're looking for. We're looking for velocity. But again, this is just equal to mv squared over r, so let's plug in that. Again, m is 0.08 times v squared over, and what's our r? R is 85 centimeters, and remember, always convert to meters. That's the standard unit we're using for all these equations. 0.85. So what is v? Well, v squared equals 1.216 times 0.85 by 0.08, and then v is just square root of that. So 1.216 times 0.85, 0.08, 12.96. Let's find the square root of that. Here's 12.92, and then v equals square root of that, which is 3.59. Yay, we have found the speed of the ball. Or almost. We found the magnitude in actually these directions. There's no angles, so there's no trick question. It's just 3.59 again. So speed is going to be, in our case, in speed, we've been using units. It's going to be, it's always meters per second. That's always nice. Oh wait, did we even find? Yeah, so meters per second. I think, yeah, so meters per second, and it's moving left. It's moving up and left, basically. Yeah, so we'll just say left, because that's essentially where it's going, because this is at the bottom. So we have that. Yay. Is it moving counterclockwise or clockwise? Doesn't really say. Whatever. We'll say left. So that's how you find the speed of, oh wait, no, what am I saying? Sorry, it's a speed. Speed is magnitude, so yeah, that's all you have to find, 3.59 meters per second. That's our answer, because that's the magnitude of velocity, which is speed. So again, another pretty simple problem, as usual, everything based off F equals ma. Let's do a spaceship problem. Spaceship completes a circular orbit of radius r is 2.0 times 10 power 7. So remember again, if you see anything with space, you look at this equation. Fg equals g little m times big M over r squared. Basically the gravitational constant, shown right over here, times the smaller mass times the bigger mass, and all that over the distance between them squared. I don't know why it's called radius. Oh, yeah, because, well, radius, forget what I said. Yeah, so it's just over the radius squared, which is equal to our force of gravity. And the interesting thing is, yeah, so we'll get to the other stuff later. So let's start. We want to find the weight of the spaceship. So remember, weight of anything is the gravitational force acting on an object. So we will find the weight of the spaceship. We just need to find the gravitational force between the spaceship and the mysterious planet. Because remember something. Hey, that's your spaceship. That's your spaceship, and that's our mysterious planet. Doesn't matter how big it is. The gravitational force between them is always the same. Why? Newton's third law. For every force, there's an opposite and it's same magnitude. So the gravitational force is exactly the same. So that's essentially what we're trying to find. So what is the weight of the spaceship? So again, we want to find the gravitational force, which is Fg equals to g little m big M all over r squared. Let's write that out. Fg equals g times m r squared. Yeah. So what do we have? We have little m, we do not have big M yet. Unfortunately, we don't have that. That'd be nice to have. But we have the radius and we have big G. So we need, so of course that means we need to find FG and we need to find big M. So, which ironically is also level 12, so that will give us perfect. So remember, you have two unknown variables, so you're going to need another equation. So let's look at what other we have. Oh wow, we have the period. So let's look at our stuff and say, well, which one of this is useful for us? And if you notice the velocity, yeah, the velocity could help, I guess. We could find the velocity. And why would that be helpful though? I guess, let's see. We want to find, yeah, so this is recording, so yeah, hopefully. So yeah, what it is, so basically, remember that in the end, since this is again going in a circle, we look at the circle stuff and we remember the centripetal force is equal to, right, m times ac or mv squared over r. And in our case, centripetal force is the force of gravitation because it's the force going like kind of into the center, and that's centripetal force. So we have these two, but again, now we have another variable v, so we need to find what v is, and v is 2 pi r over t. So we start with the power of v, so we need to find what v is first. We have 2 times pi times radius, which is 2.0 times 10 to the power 7. All that over the period being 2 hours. So just use hours. Well, now let's look at Batman. 2 hours, and let's find what v is. Well, we can cross that out, which nicely. 2 times 10 power 7, all that, times pi is essentially 6283185.07. So we have that. Now we're going to square that, multiply times mass, and divide by r. So let's just divide that by r first. So much easier. So our first squared. So this squared divided by the radius, which if you remember is 2.2 times 10 power 7. So divided by 2 times 10 power 7. So using this equation, we've got Fg equals the mass, which is 1 times 10 power 8, so 10 power 8, times basically 197392088. So force gravity is going to be equal to 10 power 8 times that. So it's basically 1.97 times 10 power 16. So we have, so now we're trying to find, so we found the weight, or we found the weight of the spaceship. It's this, because that's the weight of the spaceship is just the gravitational force. So that's our first, so that's the weight of our spaceship. Now let's find the mass of our big one, so basically big M. So you just do this equals the big G, which is 6.67 times 10 power negative 11, 0.67 times 10 power negative 11, times basically 10 power 8 times big M over 2.0 times 10 power 7 squared. So let's do this thing times 2 times 10 power 7 squared divided by 6.67 times 10 power negative 11, then divide all that by 10 power 8, and we get big M of 1.18 times 10 power 33. That actually seems kind of big, so I might have made an arithmetic here somewhere. But again, the concept is the same, and everything as usual is based off the power of F equals ma, which is, because that's essentially what centripetal force is saying. Centripetal force is saying F equals ma. The difference is the a in this case is not much like it's basically the centripetal acceleration, which is v squared over r, which is why centripetal force is m times v squared over r, because F equals ma. All right, that's that. Yeah, that's basically it. If you guys have any other questions based like for this, you can leave in the comments. And I probably didn't teach that well, It's the first time. I will try to do better next time. So, thanks. Bye.